This is Lab 2, Lines of Charge by Sujit Manigati. Uh, in Lab 1, we found that the charge of a tape strip represented as a single point charge was going to have an approximate charge of negative 1.2 times 10 to the negative 8 coulombs. But the purpose of this Lab 2, is to find a more precise estimation with integration. And we modeled the tapes as a distribution of charges, and skipping ahead to the results, we found that the with this, it had an approximated charge of negative 5.98 times 10 to the negative 8 coulombs. The concepts and ideas used for this lab were Coulomb's law and distributed charge. The procedure to create this experiment was the exact same as lab 1, so I'm not going to go too far into it, but we just created two U strips of tape and then made sure they're negatively charged and then put them next to each other so that one of them would float and then recorded that vertical distance. There are some new model in this model. There's a new model and some new assumptions for this lab. I split the tape charge into n number of charges, each with small q equals q, which is the total charge divided by big N, and the precision increases with subsequent n increases. Some necessary assumptions to make are that the charge is distributed evenly among the tapes hold the same charge, and that there is no air resistance. Uh, The the values you see on the screen are from lab 1. The tape length was 0.216 meters, tape width was 0.0225 meters, vertical distance was 0.025 meters, and in the previous lab we found that a single point charge was negative 1.2 times 10 to the negative 8 coulombs, and we used Coulomb's law. Uh, but in order to do the distributed charge calculations, I assumed lab 1's charge was correct, and that I also used integration to add up individual point charges to find the new force, and I used GlowScript to do the calculations for me. Here is the function to create each individual line of charge. Here's the function for calculating the fields and the forces of each individual DQ point charge integration method. And here's the code for adjusting the tape charges. Uh, The main effect I want to explain is how the precision of electric force calculations gets better as n increases. The first picture you see is when n is equal to 10, and as you can see, there's a big gap in between the charges, so it's not as precise of a calculation. And as n gets to 50, you're calculating more charges within the same area, so the calculation becomes more precision, is a lot more precise. And I just wanted to try for fun, but I set n equal to 150 and n equal to 200, and as you can see, there's a lot more arrows, and that means that it's a lot more precise in its calculations, and as a result, you get more precise calculations. As a result, as n increases without bound, the estimation becomes more precise, and this can be done easily because we have access to GlowScript and VPython because the computer can add up numerous numbers efficiently rather than doing it by hand. And so as a result, if I had modeled the tapes as a single point charge, this would just result in the answer from lab 1. And so the single point charge would be negative 1.2 times 10 to the negative 8 coulombs. But with the distributed line charge, I get an answer of negative 5.9 times 10 to the negative 8 coulombs. And that is drastically larger than just a single point charge. Uh, These estimates are different because the distributed line charge model takes into account more smaller charges and adds up multiple charges to find a total. And as a result, it's going to be a lot more closer to the real value than just two single point charges because we're using a more specific realistic model, and we're removing the assumption that the tapes are just a single point charge, and now we have them as a distributed charge like a line charge model.